Alright, so in this video we go over section 5.3 properties of a rational function. So we are going to review how to find the domain of a rational function, and we are going to use that as an idea to find the asymptotes of a rational function. So first of all, let's find the domain of a rational function. So a rational function, recall that it's a function of the form p of x divided by q of x, where p and q are strictly polynomials. So these two have to be polynomials in order for a function to be a rational function. Otherwise, if you have like a polynomial divided by a radical, well, that's not a rational function. All right, and here the little caveat here, the red flag about this type of functions is that q, the denominator, cannot be 0. So we need to exclude those values for which the denominator q is 0. So this is what we do. So in this case, let's observe this function and let's find the domain of it. So I'm going to focus on the denominator of this expression only, x minus 5. So I'm going to find out what x minus 5 is not a 0, so x cannot be positive 5. All right? X cannot be positive 5. Because otherwise, if I plug in positive 5 over here, the denominator is going to be 0. And let me fix this. Got something weird here. All right. So 5. Alright, so that means, okay, let's write this using interval notation. I cannot take the number negative 5. So I'm going to have an open circle for negative 5. Alright, I'm going to use this to help us find the domain using interval notation. So the function will be good at all these stages in which I'm shading, except at negative 5. So in this case, negative infinity to negative 5 union, or actually positive 5. Again, I did the same mistake. Let me erase the negative right here, and let me erase this other negative there. All right. So that's using interval notation. Then using set notation, x such that x cannot be positive 5. So the two notations we use here. Alright, for letter B, so notice the denominator has the form of a difference of squares. So if necessary, we need to factor those difference of squares. So let's write it down like 1 over x plus 2 times x minus 2. Okay, so in this case, I'm going to set this guy equal to 0. That's going to give us x equals negative 2. And this is going to give us x equals positive 2. So in this case, the reason for which I'm going to highlight them, because those are the ones that we don't want. All right, we don't want x to be negative 2 or positive 2. Okay, so negative 2, positive 2. And I'm going to shade only these three intervals. So it's going to be negative infinity to negative 2, union negative 2, positive 2 rather, and union to the positive infinity, which in set builder notation we would write it, we would express it as x cannot be x such that x cannot be negative 2, comma x cannot be positive 2. So those are the two ways to express the domain: interval notation and set notation. Okay, what about r of x equals x cubed divided by x squared minus 1? Well, in that case, let's find out. So in this case, we have x squared plus 1 in the denominator. So let's find out whether we have restricted value. So in this case, if we try to solve this equation, x squared cannot be -1. Well, in this case, if we try to solve this, we get plus or minus the square root of -1, which is plus minus I. However, in this case, we don't want imaginary numbers, we don't want complex numbers. So in this case, there are no restricted numbers. So domain for this function will be all real numbers. If you plug in any number in the denominator, it's never going to be 0. The alternative, x such that x belongs to the set of all real numbers. Okay? Now let's look at this one at letter D. And you need to be very, very careful with letter D. In fact, I'm going to put a star here. So watch when you have something like this. So number one, if we write this in simplified form, notice how we can factor out the difference of squares as x plus 2 times x minus 2. And then divide by x minus 2. You are going to notice something interesting in this case. Notice how the x minus 2's go away, they divide out, and we are left with only x plus 2. Alright, so well, when you simplify the function, you get something with no more denominators. So you may think, oh, the domain is all real numbers. Well, because this function x plus 2 came from something that had this x minus 2, well, we need to consider the domain excluding the x equals 2. Alright, so in this case, 2 and shade everywhere else. Okay, so the domain will be using interval notation, negative infinity to 2, union to the positive infinity, using set notation x such that x cannot be 2. Right? So careful with these cases again. So when you simplify them, even though we divide out some of the factors that potentially give a denominator equals 0, okay, this, if we were just given f of x equals x plus 2 without knowing this, well, x plus 2 is the domain is all real numbers. However, this x plus 2 came from simplifying something more complex like this rational function. Alright, so let's see. Let's move on to the next page. And let's find asymptotes, vertical asymptotes first, and then horizontal and or oblique asymptotes. Alright. So we need to have a rational function in the lowest terms possible. And then we're going to have a vertical asymptote if r is a real 0 of the denominator q. In other words, the factor in the denominator of the form x minus r will tell us that x equals r is the equation of a vertical asymptote. Okay, so we need to be very, very careful when finding vertical asymptotes, because if the rational function is not written in the lowest terms, then the theorem here would be applied in an incorrect form. Now, there is a note that I want to add here which is not explained in our textbook. So sometimes we are going to have factors that divide out, like the one we had earlier here in the previous example. Notice how one of these factors divided out, but in that case the function has a hole. The graph of the function has a hole at that value of x. Well, I'll show you more in detail about those holes that function has. Okay, Find the vertical asymptotes if any of the graph of each rational function. All right, so let's see. So those are finding vertical asymptotes is going to be very, very similar to finding the domain. So in this case, the denominator factor is x minus 6, set it equal to 0. That means x equals 6 is a vertical asymptote. I'm going to use VA for short. VA stands for vertical asymptote. Let me write it down first, and then later I'm just going to use the short version. What is a vertical asymptote, by the way? A vertical asymptote, so when we graph this, it's going to be, well, at x equals 6, 1, 2, 3, 4, 5, 6, 7, 8, it's going to have this dashed line, which, by the way, calculators are not going to show you those asymptotes. So let me give you an example using the graphing calculator. So x plus 3x over x minus 6. Be sure to open parentheses, x plus 3, close parentheses, divide, open parentheses, x minus 6, close parentheses, and graph. See how this is going to look like, right? So it's going to look a graph like this. All right, the asymptote would be somewhere here. I'm going to write on the screen of my calculator. Okay, so that's the value the function cannot take. All right, and it's coincident with the values for which the rational function is undefined. All right, so let's do letter B. Look at the denominator, x squared minus 25, set that equal to 0, factor, solve this polynomial equation by factoring x plus 5, x minus 5. That means the vertical asymptotes are x equals negative 5 and x equals 5. From here we get this answer, and from this one we get the second answer. Want to verify that using the graphing calculator, and you might want to do that. So go to y, and so that's we delete, and that's x squared. Whoops, x. Whoops. This is not going right. Oops. X. Oh, come on. There's a mess going on here. Divide that by x squared minus 25. And close parentheses and graph. So you will see the graph like that now. Well, again, keep in mind that your graphing calculators, yes, it's very smart, but not as smart as to show you the entire graph in the one place. And on the other hand, it doesn't show you the asymptotes. Okay, those we're going to do them by hand in the last section of this chapter. Okay, what about h of x equals x squared plus x squared divided by x squared plus 9? So in this case, x squared plus 9, set it equal to 0 to find those vertical asymptotes. And it turns out we get imaginary numbers, so that means no vertical asymptotes. No vertical asymptotes in this case. Okay, let's verify that using the graphing calculator, of course, why not? So that's second insert. I'm gonna second insert squared, whoops, Let me just clear x squared divided by open parentheses x squared plus 9 we said, right? So x squared plus 9 and graph. So notice we're just going to have a continuous function. In fact, it doesn't have any vertical asymptotes. The domain, if you look at it, it's all real numbers. Right, what's going to happen with letter D? Letter D, it's going to be an interesting one because, okay, number one, let's simplify, let's rewrite the function by factoring this. Okay, so x squared minus 9 factors as x plus 3 times x minus 3. And the denominator factors as well, factors of negative 21 that add up to 4. Well, let's see, I would say plus 7 and minus 3. 7 minus 3 equals 4. 7 times negative 3 equals negative 21. Now, notice something interesting, and I'm going to highlight this. The factors that actually get canceled right here. I'm going to cancel with a mild color, not with a really dark color. So I'm going to end up with x plus 3 and divided by x plus 7. Well, so in this case, the legitimate asymptote will come from the denominator of whatever we had after simplifying. So in this case, this is the vertical asymptote, okay? This is the vertical asymptote. All right, however, the factor that got canceled here, I'm going to use a different color here. On this x minus 3, set it equal to 0. And x equals to 3 will be the equation of the whole. Okay, so in this case we have a whole. Whole at x equals 3. Vertical asymptote is going to be like that. So now let's see how that looks like. All right, so I'm going to type, be clear, x squared minus 9 divided by x squared, oops, need to open parentheses first, x squared plus 4x minus 21. Okay, close parentheses and see the graph. See how the graph only shows you the only one vertical asymptote at x equals negative 7. It's right there. However, just the same way that a graphing calculator doesn't show you those dashed lines called vertical asymptotes or horizontal. Actually, this one has horizontal asymptotes as well. We're going to look at those in a couple minutes. And in this case, there is a whole at x equals to 3. 1, 2, 3. Which the graphing calculator is not smart enough to show you. Well, it's too big. Let me use a nicer color like this. Okay, well, it's not. So that's how the graph should have looked like if the graphing calculator were a really nice device to show you everything. All right. So in this case, so we're going to have more like this when we get to the later section in which we are going to look at graphing rational functions. Okay, now let's look at the other type of asymptotes. Horizontal or oblique asymptotes of rational, I'm sorry about that, of rational functions. All right, so let's first define whether rational function is a proper rational function or improper rational function. So a rational function will be proper if the degree of the numerator is less than the degree of the denominator. Otherwise, the rational function is improper. Okay, and over here it's all the different property that we consider when it comes to find the all the possible horizontal or oblique asymptotes. So we need to keep in mind all these 1, 2, 3, 4 points. Okay, number one. The number one point is when m is less than m, that is, the degree of the denominator of the numerator is less than the degree of the denominator. Again, keep in mind that the form of a rational function is this. We have a polynomial in the numerator and a polynomial in the denominator. All right, so these are the constant terms of the constant terms of each polynomial, and each number right here, it's very important to identify, that is the numbers that multiply the highest degree term in each numerator and denominator are the leading coefficients of them. All right, so let's see. If the degree of the numerator is less than the degree of the denominator, then we are going to have a rational function and the graph will have a horizontal asymptote y equals 0, and we're done. We don't have to do anything else. We don't have to do a polynomial long division or ratio of leading coefficients, which is what we do after in the next descriptions. Now, number two. For number two, well, we're going to have three cases when the degree of the numerator is greater than or equal the degree of the denominator. Okay, let's look at case A, in which the degrees are the same. When the degrees are the same, then the line y equals an over bn, that is ratio of leading coefficients That's all we do. Find the ratio of the leading coefficients, and that's going to be the horizontal asymptote. All right. And the next case, when the degree of the numerator is one more than the degree of the denominator, then we need to do polynomial long division. And in this case, our asymptote will be oblique. It will be a diagonal line of the form y equals ax plus b, or mx plus b if you will. Okay, by the way, this a and b do not have anything to do with the coefficients here, all right? So in this case, those are found by performing polynomial long division. Now, there's another case in which the degree of the numerator is either 2 more than the degree of the denominator, then the quotient, then in that case there's no horizontal asymptote and there's no oblique asymptote. It's other types of weird asymptotes that we may not even cover in this course. Okay, let's look at a couple of examples. So, find a horizontal or oblique asymptote if they exist. For the function r of x equals x squared plus 6x plus 2 divided by x cubed minus x, there's a little typo here. This is supposed to be squared, not x to the x, and minus 5x plus 1. Okay, in this case, every time we have a question like this, we need to look at the degrees of the denominator and the numerator. And in this case, we can see that the denominator of the degree of the denominator is greater than the numerator's degree. So in this case, it will fall in the first category, and the only asymptote is y equal to 0. There's nothing else we have to do here. The next example, find horizontal or oblique asymptote if one exists. So in this case, we have the quotient of two polynomials which have the same degree. All right. So in this case, this will fall in category A of the second part, in which all we do is look at the ratio of the leading coefficients. So y will be a sub n divided by b sub m. In this case, let's label which one is which. So this number 8 will be our a sub n, and this 4 will be our b sub m. So in this case, the ratio between 8 and 4, which equals to 2. So y equals to 2 will be the horizontal asymptote. All right. Let's look at another example. Let's look at the last page of this handout. All right. So example 5, find the horizontal or oblique asymptote if one exists. In this case, notice how the degree of the numerator is 1 more than that of the denominator. So in this case, our asymptote will be of the oblique form, and in this case, it's obtained by polynomial long division. So let's go ahead and do that. So I'm gonna write this in division form. And again, keep in mind to put placeholders. So x cubed minus x squared plus 0x plus 1. And then inside of the division box, I'm going to have 3x to the fourth plus 0x cubed minus x squared plus 0x plus 0. Okay, so let's divide leading over leading. 3x to the 4 divided by x cubed, that's going to give me x. 3x rather. I'm going to multiply 3x times x cubed. That's going to give me 3x to the 4. Remember to change the sign. Two positives is positive, changes to negative, and then 3x times the negative x squared. That's going to give me negative 3x cubed. But again, that's going to be changed to positive because negative times a positive is negative. Change that to positive. All right. So in this case, 3x times 0x, that's going to give me 0x squared. And 3x times 1, that's going to give me negative 3x. Okay, two positives, we change it to negative. All right, so let's see. So in this case, we can cancel this out. 0 plus 3, that's 3x cubed. Negative x squared plus 0x squared, that's minus x squared, and then minus 3x, and then drop the 0. Okay, we drop the 0. So again, we do the same. Let's divide these two leadings. 3x cubed divided by x cubed, that's going to give me plus 3. Okay, and guys, in this case, you don't have to keep going for the rest of the division because we already had the quotient. Okay, so the moment you get the quotient, you don't need to do the rest, because I'm not asking you to show me a polynomial long division. I'm just asking you to find the quotient. But if you want to do that's 3 times x cubed and negative 3x cubed, and then plus 3x squared plus 0x, and then minus 3. Boom, boom. And then negative x, actually 2x squared minus 3x, and then minus 3. So that's the remainder. Okay, that's the remainder. So the oblique asymptote will be of the form y equals 3x plus 3. Okay. Now, number 6. Find the horizontal or oblique asymptote if one exists for this one. All right, now look at the degrees. The degree is 5, the degree is 3. In this case, this falls into the last category. The degree of the numerator is 2 or more greater than the degree of the denominator. So in this case, neither horizontal nor oblique. Nor oblique asymptotes. Okay, and this is the end of this section. See you on the next video.